3, 4. So I'm it. Is that just because it's Friday, or Monday and Wednesdays do you have classes too? Yeah, but wow, so I'm it. Well, then thanks for being here. So I usually don't go out of town for this weekend, but I am this time. But I'm not leaving for a while. So. All right, friendly reminder, because it's the first one. You guys got lots to remember with all your other classes and life in general, but you have 2 homeworks due. When? At what time? Yeah, Sunday at 11:59 p.m. Remember, if you save your progress as you work on your homework, worst case, you can't submit it because you forgot or your computer dies or the network's down. Your last saved answers will be the ones submitted. So that's always good to at least save progress as you go. I did notice several of you have been on there working. So I can see everything you're doing. Those of you that have already submitted your answers, kudos to you. I feel a little guilty, though, because I haven't covered everything in lecture. There'll be several things today. So I could have helped you, but hey, some of this you already know, some of you don't. That's why you have 2 friends, let alone you guys as friends. What else? Anything? Don't come to class Monday. Won't be here. And in case some of you were worrying, I talked about pre-lecture questions. So in theory, we would have one next Wednesday, but I was thinking, it's a long holiday. We haven't done it yet, and you'd have to do that before we meet again. So it will happen next week, but until we meet again, you only have to worry about those 2 homeworks. I'll lay that on you later. But you should have your clickers by then, because I'll start using those, and they'll be for points. Any other questions? Hey, did you find the superhero paper? In the resources in WebAssign, there's a PDF calendar that shows what we're studying each lecture and when homework's due and superhero due dates and final exam and blah, blah. There's also a superhero rubric, how I'm going to grade it, so you can see exactly where the points go. A sample, a past student agreed to let me share her paper that she wrote. It was several years ago now, but I thought it was a good example of what I'm looking for, so that's there to help you. Syllabus. There's something else that I'm not thinking of right now. There's like 6 files or something there, but they're there for you and WebAssign. Did you guys notice anything this week in the world around you? I don't make a note to do this, but I like doing this. Usually I find I do it at the end of the week. Like in physics is all around us in the world. Is there something you observed or thought was cool or saw and wondered what was going on? Even if it has nothing to do with what we're currently covering? Yeah. They did? Ooh, that would be a big thing. They actually think they did it, huh? I hadn't heard that. A gravitational wave. We're going to study waves. Your brief little bit is you have particles, matter. We've been talking about mass, but then they interact with each other. And there's these interacting particles. Photons. You might not have heard of the term, but it's light. Some people define light as photons. And it's this interacting particle that can go between things. Another one, electric fields. You've probably heard of those. Between charges. The weak field and the strong nuclear force. You might have heard of those. Well, gravity, they predict that there's this graviton, this interacting particle. And so they predict that there ought to be a gravitational wave, but we've never been able to detect it. So this would be a big advance if that's validated. So there's an observation. They have proof. They went through the scientific method. They're hoping to prove this fact. So now what do scientists need to do? Yeah, they need to test it and see if they have the same observations of that phenomena so that we can say it's a fact and start building up and become a law or eventually part of theories. actually it's already part of a theory. They're just trying to detect it, but it'll be another plug to support current theories. But that's going to happen before a lot of people believe it. Yes. The mass of the Earth changes? Do you have any ideas why that might be? Yeah. Radiation does come from the sun and interacts with us. The Earth itself is alive and acting. We have an atmosphere and things are coming and going all the time. The Earth radiates and is giving off radiation, and it's absorbing at the same time. Is it always in balance? No. A crude example is, do you think your mass always stays exactly the same? I mean, you're drinking, you're eating, you're exercising. It's always fluctuating. How many of you ever try to weigh yourself? And from hour to hour, it seems to be different. It's kind of like that with the Earth. There's these processes going on all the time, so it can change. I mean, that's one answer to that. So yes, I believe that. So in general, if you have some queries or hear something, read something, see something, I hope you feel free to bring it up. It'll help all of us, I think. All right, we're in chapter 2. I should finish today. I better. There's very little left. It was on Newton's first law about inertia. How would you define inertia now? You got to explain it to your mom. What's it? Yeah, I've been studying about inertia in physics class. Well, what is that? And you tell her what? I failed. Resistance to a change in motion. I like that. That's how I define it. That's how I remember it, so it makes sense when I'm trying to. And, oh yes. Or to keep itself at rest. Good. And a lot of people, in science it makes sense, but to the layperson, state of motion implies it must be moving. In science, it could be at rest or moving. So we ended with equilibrium. I just talked about that. Your book defines equilibrium as a state of no change. It's not changing its state of motion. So this book, would you say it's in equilibrium? Yeah, now. Is it now? How do you know? What's changing? Yeah, we're going to get into chapter 3. When we say if consistent, if what's constant? There is this thing, dynamic equilibrium. That's basically, it can be in equilibrium while it's moving. It's possible. There's no change. So we're going to have to define this change. I'll go ahead and jump to it because it leads into chapter 3. When we say inertia is a resistance to an object wanting to change its state of motion, that state of motion is referring to its velocity. You guys know that term. Velocity, how fast it's moving. How do you change someone's velocity? Somebody's heard of it. You exert a force which causes it to accelerate. Acceleration is a term in chapter 3 that causes a change in velocity. You know, when you hit your accelerator on your car, that's why it's called an accelerator. It changes your velocity. You increase your velocity. How about when you hit the brake? What are you doing? You're decelerating. Or in science, we call it negative acceleration. You're accelerating in the opposite direction. And your velocity decreases. It changes. So that's two ways you can change your velocity. Speed up or slow down. But they're both acceleration. They both change velocity. They're both changing your state of motion. And both of those require a force to do so. Otherwise, you're happy maintaining that state of motion, that constant velocity, forever. unless something causes you to change your motion. So, you don't know exactly, but if I'm moving this and I'm trying to move it at a constant velocity, now what do you think? Would you say it's in equilibrium? Oh, you guys not so sure now. Yeah, direction. I haven't got that one yet too, but we'll leave that for now. If I'm applying a force on this such that it's not accelerating, if it's not accelerating, its velocity will not change, correct? If its velocity is not changing, it's not changing its state of motion, and we'd say it's in equilibrium. And yeah, you can specify that as dynamic equilibrium because it's in motion, as opposed to static equilibrium. It's not moving. They're both equilibrium, though. I think there was a question on the homework of, let me grab something. This will work. All right. You toss a ball up in the air, and at the top, for that brief moment, right there, it stops for a moment. It's going up, it stops, and then comes back down. And I think the question asks something like, is it in equilibrium at the top? Why do you say that? Gravity's working on it, but it's not moving. There's a force on it. Do you remember at the end of last class, another way I explained that if something's in equilibrium? We just covered that equilibrium is no change in motion, which specifically velocity. So the velocity is not changing. No change. Which means the acceleration is constant or zero. That's zero. You started to say something over here?
Well, because the force on it would be constant, so it would be in equilibrium. Because all the velocity and acceleration would be zero, and gravitational force.
Yeah, I just made a mistake. He's picking up on it. I apologize. I'm going to correct it. But does anybody else? That's because I haven't defined. Let's just do this. In chapter 3, you got position. I think you know what position is. So, any questions? Speed. Speed is how fast you're going. I'll say moving. In physics, a little more specific, let's say positions like x. You're changing your x position. You can define it as the change in position with time. That's your speed. You might be moving so many meters every second. That's the units for speed, meters per second. There's miles per hour and things too, but these are the units, the standard units that scientists use. That's what we'll use in class mostly. So you can see it's the rate at which you're changing your position. So moving has another connotation there. Rate of changing position. This will help us. He saves them for chapter 3, but I think it's going to help us understand equilibrium better. So, does that make sense? 50 miles an hour. You're going to go 50 miles in 1 hour. It's the rate you're changing your position. There's something called velocity, and gee whiz, that's the same thing, except what do you think is different? Somebody said something, but direction is correct. Velocity is a vector. Don't want you to think I'm writing V stands for vector. S is for scalar. There's a nice coincidence. Speed is a scalar. It's just magnitude only. 50 miles an hour. So who cares which way you're going? Velocity is a vector. It's 55 or 50 miles an hour north, or that way, to the right. So it has a direction. Thus, somebody said, I think it was you, there's 3 ways to change your velocity. You can speed up. You can slow down. Those make sense, right? You can also turn. If you change your direction. So if I go 50 miles an hour around the curve, I'm still going the same speed, right? 50 miles an hour. But I'm changing my direction. Since velocity is a vector and includes direction, I must be changing my velocity. And you guys now know, whether you realize it or not, in order to speed up, you got to accelerate. That requires a force. In order to slow down, you got to decelerate or accelerate that way to slow you down, your velocity. So it must require a force and an acceleration to turn. If I'm changing my velocity, that requires an acceleration. You've probably heard of it, centripetal acceleration or centripetal force. I won't define that now, but most of you have probably heard of it, and so it's still required. So there's 3 ways to change velocity. And so if you're changing your velocity, that gives you an acceleration. That's the change in velocity with time. It's in meters per second is velocity over time per second. You can think of it this way, meters per second, or you often see it as meters per second squared. So in this class, I'll often say meters per second squared or meters per second to help us remember this concept, because it's a conceptual physics class. So if you're going 50 miles an hour and you hit the accelerator and you accelerate at 5 meters per second squared, that means every second you will increase your velocity by 5 meters per second. A little, say you're starting at 50 miles per hour. That's your velocity. If your acceleration is 5, I changed my miles per hour squared. We'll just stay in this unit for now. Miles. That means every hour, after 1 hour, how much faster will I be going? 55. I'm going to change my velocity. Acceleration changes the velocity by 5 miles an hour every hour. It's 5 miles an hour every hour. So after 1 hour, I'll be going 55 miles an hour. How about 2 hours? 60. 3, 65. That's all acceleration is. It's this change in velocity. It just tells you the rate at which you're going to speed up or slow down or change direction. And this is a vector also. It has direction, because you can accelerate that way or that way or that way or that. It matters. And to get an acceleration requires I've said it lots of times, a force. That's going to give an acceleration. So this is where I messed up. If your force is non-zero, you must be accelerating, right? You with me? If you're accelerating, what are you changing? Your velocity. If your velocity is changing, are you in equilibrium? No. So that's where I messed up. If you're in equilibrium, it does indeed mean you're not changing your velocity, which means the acceleration must be 0 because it's not changing. If this is 0, this has to be 0, or vice versa. And if this is 0, what does that tell you about the forces? And this is where I wanted to get to. They'll be 0. Are there no forces? They cancel each other out. So what we do know, you just figured out, that thing I called F net, the combination of all the forces, in case there's more than one, that must be 0. So that's how you, 3 ways you can think of equilibrium. The net forces must add up to 0, which means there's no acceleration. We're not changing our velocity. We're in equilibrium. So this, not moving. Acceleration 0. Equilibrium. If it's moving at a constant speed, it's not changing its speed, it's not changing its velocity, so its acceleration 0. But am I applying a force to it? Yes. I'm pushing it, right? There's a force. So how can it be in equilibrium? I drew it that way, so I'm pushing it. Yeah, I can be constant. I'm being pretty, well, actually I'm not. But, okay, what's the net force on the book then? Net force, you just add up all the forces. How can it be 0? This is the only force. If that was 0, I wouldn't be pushing it. Yeah? See the conundrum here? This is where you start reasoning. What else do you know? You just don't realize it. Just think in terms of your gut. Okay, I'm pushing this. I'm applying a force. We got that. But is it accelerating?
No. When you start, yes.
When I start, yeah. So what's keeping it from accelerating? Bingo. The table exerts friction on it. And which way does it push? Point. It always retards the direction of motion. So it's that way. That's next chapter too, or we're getting there. And here's a vector arrow. How long should I draw it? It's this way. The same length? So, friction. And somebody said, because they knew air resistance too. I'm not going that fast, so it's negligible. I won't include it at this point, but you're right. Okay, if those are the same and we sum up the forces, all right. By default, scientists, for convenience, usually say to the right is positive or up is positive. You can define it however you want. Just don't change it during the same problem. So for example, my push is to the right, so it's a positive force. F of push. And we add this one. It must be negative. It's a vector friction. So I wrote it fancy like that, but you can rewrite it. It's essentially just the push is positive minus friction going the other way. So I'm trying to accelerate it to the right, and friction's trying to accelerate it back to the left. These must be equal because we know those add up to 0. That means the net force is 0 because it was not accelerating, which means the change in velocity is 0. And we can say it's in equilibrium. And in that case, dynamic equilibrium, because it is in motion. Think of your car again. You're going 50 miles down. No, this is Utah. You're going 80 miles an hour down the highway. But you're maintaining 80 miles an hour, right? Cruise control. All right. Are you accelerating? So automatically, you know the net force is what? 0. You're in equilibrium. But wait, you know your foot's on the gas. There's energy being expelled to push you forward. You're pushing the car forward. Why aren't you accelerating? Same reason. There's friction in it, and now you're going faster. It matters. Air resistance pushes back. If we threw in air resistance, resistance, that's easy. You just add it right here. Minus air. So you got one force going this way, and you got two going negatively in this case. That's how you just add up these forces. And here, this is your free body diagram. We're drawing a picture to help us remember what's going on here. And then you just balance in the forces to figure out what's happening or what its state of motion is. Questions? You forgot about throwing the ball up. So let's revisit this. Right at the top. At the very top, what forces are acting on it? We need to figure that out. Gravity, I heard. Say again? Its position is changing, yes. So I heard gravity. Let me do that. Which way is gravity? All right. Force of gravity. And it is changing its position. Sure. Mechanical. Yeah, pushing is a mechanical action. Yeah. Technically, yes. My muscles. There's lots of little things going on in my muscles combining together to push. Yes. I'm going to answer it this way. If I'm interested in a book, then I can simplify this by just what force is acting on. And so just sum that up by what happens there. There's other things and other forces and energy going on in your muscles and converting of chemical food energy and whatnot to make that happen. But that's over here, acting in my arm and on my muscles. The ultimate result is it makes my hand move, and my hand is what interacts with the book. So, and this is important because it'll help you in some of these questions. When you want to know what's going on with this object, you only need to concern yourself with the forces acting on this object. We're going to start asking now, like this, what are the forces acting on things? And you can start naming all these forces as you learn them. And there's a lot more out there that we haven't mentioned. But we really only need to look at the forces on the object in question at that moment. So it's a good point. I'll reiterate that again when we get to Newton's third law. So back to this. Are there any other forces acting on the ball at the top of its path when it momentarily stops? Force of it going up? What's applying it? Yeah, I exerted a force on it to make it go up. Good. As soon as it leaves my hand, though, I'm no longer pushing it. It's kind of like the puck. I exert a force to accelerate it. State of motion, velocity 0. I'm going to get it up to some velocity, so I must accelerate it initially to get it to a velocity. So I'll apply a force. But now, other than this, it goes at a constant velocity. But so it's still moving. But I'm not applying a force to it anymore. So the same is true when I toss the ball up. I do apply a force as I'm getting it up to speed, but it leaves my hand with a certain velocity, and I no longer push it anymore. It goes up on its own. Slows down, and then speeds back up this way. So I'm glad you said that, because I am, at the top, not exerting a force on it. Does that make sense? So do you think, are there any others? This might be it. What do you think? Air resistance.
Would it be on what's at the top, though?
This one we don't even have to simplify. When things are moving, they meet air resistance, but at the top it stops momentarily, so it's not moving for that brief instant. So air resistance, we can't even consider that one. So this is it. So what's the net force? Net. You just sum them all up. Okay, we got, if we say, up is positive, then we have a negative gravity. We're done. That is the net force because it's the only one. So are we in equilibrium? No. Do you guys see why it's a no? Because the net force is not zero. It is accelerating. So how can something be accelerating and not moving? It's changing direction. I mean, you guys know this. It's just like your car going at 80 miles an hour, right? And then you slam on the brake. Which way are you accelerating? That way. Which way are you moving? You're still moving forward. That bothers people sometimes too. Well, sure, you have inertia. You want to keep moving at 80 miles an hour. And it takes something to slow you down, but you don't do it in an instant, right? I hope not, or you're dead. So yeah, your velocity decreases. And as long as you could keep accelerating that way, not through a brake obviously, you'd stop and then start speeding back up in that direction, wouldn't you? So that's what's happening with gravity. Gravity is being applied down on this all the time. It's acting on it right now, correct? The Earth's pulling it down. Why doesn't it fall? I'm exerting a force, a support force, your book calls it. Scientists also call it a normal force because it's perpendicular to the surface. For clarity, we'll do it like this. I'm exerting a force up. Earth's pulling it down. We know they're in balance because it's not accelerating, so it's in equilibrium. The forces are equal, but opposite in direction. When it's in the air on the way up, like now, is Earth still pulling on it? Sure. That's why it slows down. And then it pauses, and then it speeds back up because it's still pulling on it. That make sense? So the net force is never zero once I let go of it. It's never in equilibrium during the toss. You sure? Groovy. We covered a lot there in that example. I like when we can do it that way instead of me just, and now we have this, and now we have this. You got to see another force body diagram examples. Here, that one was it. So how does it get accelerated in the first place? Both of these. Let's go back to this one. If friction is applying, how would I make this move faster? So I'm going along, we're happy. How do I speed it up? Yeah. If this force is a little bigger. Well, the way I've drawn it, let's see. Let me read. I currently have friction written down as well as some air resistance. So, all right, magnitude. This one gets to there. This one, if we add it to it, gets to there. So can you see the sum of these two in the left direction? I'd have to apply a force that much to make it in equilibrium. Are you with me? So I would have to be a little more than that. Because now the net force wouldn't be zero. You'd have this much as a net force. Push. That little net force is the difference in that direction. And that would cause it to slowly accelerate and increase its speed. No longer be in equilibrium. So back to you. Yeah, if I was applying a constant force the whole time, that means the force is not zero, the net force. I would be overcoming these. And it would accelerate. Good, cool, did that. We're halfway through chapter 3, actually. Do you realize that? Actually, some into chapter 4, but we'll go. Your book talks about instantaneous speed and average speed. I bet you can guess the difference. This one they match layman's terms. On a trip, on average, you could say, I went 45 miles an hour on average. But, you started at 0. You went through town at 30. You got on the highway and went 80. And then so on average, we could say you went 45. So over the total distance, what was velocity? It's still a change in position over time. You would just take the whole path traveled from here to Grandma's house. And it took, an hour and a half. That would give you the average velocity for the whole trip for that time period. But at any given instant, you could be going a certain speed, certain velocity. And we call that instantaneous velocity. So while you're on the highway, your instantaneous velocity right then would have been 90 miles an hour. But when you're going in the school zone, it was 20, right? That's your instantaneous speed. If you could get rid of all the houses and the highways and just drive straight there with nobody in your way, if you went the average velocity, you'd get there in the same amount of time. It's just sometimes your instantaneous is a little slower, and sometimes it's faster. That one hopefully isn't too difficult of a concept, but you do need to know the distinction. Free fall. No, let's. Do I want to do free fall? Let's say free fall. Let's do some velocity and acceleration to end. And before that, let me look at the homework and make sure. Did that. Oh, let me do this one. Because I gave you a couple pulley ones, and we haven't talked on pulleys. They just redirect forces. So like one of them, Nellie here, hanging from a pulley. Remember that one? People that are nodding have looked at their homework. Okay. It actually says Nellie Newton hangs at rest from the ends of the rope, as shown. How does the reading on the scale compare to her weight? They put a scale in here to read the tension in the rope on this side. So this is what I would do. We're interested in the force over here. So let's see. It's her. She's the object. There, we just simplified Nellie. Scientists like to do that. Spherical cows. Okay, what are the forces acting on Nellie? Gravity. That's her weight. Gravity. All right, what else? Tension in the two ropes. And it's in two places, right? So we have one over here and one over here. Let's call it T1 and T2. Now, something I kind of took for granted with this asking this question already, but pulleys just redirect it. It's the same rope. If you pull over here, this goes up. If you pull down a half a meter, this goes up a half a meter. Thus, I bet you know, how do you think the tension of T1 compares to T2? The tension here compared to here. They're equal. So we could just call this T and T for this setup. It's the same rope. It's got the same tension in it. Okay, is there anything else? I'll take the pause as probably not. Yes. Hanging, so not on the ground. If she was on the ground, I'd add another force holding her up. And I would call that the support force, or normal force, Same thing. That's the ground. We would just add that in. But not happening in this case. So. Yeah, that's it. So if you sum up the forces, you got T up plus T up minus your weight down. And what is equal? Yes, you do. It's 0 because she's at rest, equilibrium. So you can, if you rearrange this, you see that 2T equals Fg? They're balanced. When they're up, one's going. If you divide both sides by 2, you get T is half her weight. So this side, even though it's the same tension in both, this only has to support half her weight. This gets the other half. Yes. I'm going to leave that one to you. Okay. How about a gymnast on the rings? Same idea, right? What if Nellie Newton gymnast went like this? Or shifting her weight. Or there's some examples in the book of the painter. The painter supported by the seating, right? If you're standing right in the middle, things are balanced. I bet you can see the symmetry there. The tension here and the tension there, it's just like this. 2T up. And the weight of the person and the plank now down. But each one's about half. Can you see that? Do you agree? What, though, if they stand over here? Who's going to feel more tension? Yeah, the one on the right. There'll be more tension here than here. How much more? I don't know at this point. But I do know that T1 and T2 must, the sum of those two must be balancing the weight of this and the weight of him. Because they're in equilibrium. And you can use that to figure things out. But yeah, if you shift your weight, it's going to change things. Yeah. Yeah. Technically, it's not in equilibrium as it shifts, but once he's there, back to equilibrium. Oh yeah, make sure. It was explained more in the book. I haven't here. Let's do. How do you find weight? I've given you the info to do it, but haven't explicitly said it. Some of these ask you, well, what's their mass versus their weight? It's that formula, Newton's second law, because basically we've learned now that if you apply a force, it causes a mass to accelerate. What I haven't specifically told you, though, is the acceleration due to gravity. Earth is trying to accelerate everything downward at, we call it G, the acceleration due to gravity. And that value is 9.8 meters per second per second. It's an acceleration downward. That's the actual value. And if you need the actual value, actually, use this when in doubt. But for thinking processes, I always like to use 10 meters per second squared, because that's the same thing. It just makes mental math easier. And the homework probably accounts, I think I put in a safe zone there of number of significant figures type thing where you can use each. But when in doubt, use 9.8 and you'll be much more likely to be right. You'll be more accurate. But I'm happy with either. So if you have a mass of, I don't know, 30 kilograms. If you're made up of 30 kilograms of stuff, the Earth tries to accelerate you down at 10 meters per second squared. The Earth's pulling me down right now, right? It's trying. So if I step on a scale, what's it going to read? 300 kilograms meters per second squared. Now that gets used a lot. This is what we call a Newton, after Sir Isaac Newton. They're the same thing. A kilogram meter per second squared is the same thing as a Newton. So my weight is about 300 newtons. If I'm 30 kilograms. That's how you would find these values if you needed to. Does that make sense? I will save the velocity in this. We've got 2 minutes. I'll pick a couple more fun inertia ones. How about this one? Yeah. I got way too many inertia demos. That's the problem. Okay, this is a lead brick. It's 26 pounds. You can tell it's heavy. So I'm going to put it on my hand, and it's exerting 26 pounds on my hand. You can tap on it. Or you can just outright. And I'm okay. Who wants to try it? Who trusts physics? All right. Now, I won't lie. Putting 26 pounds on you in the first place is uncomfortable, so kind of get it. And while he's getting brave, you might start tapping just to convince yourself, but when you're ready, why does this not kill him? Why does this not break our hands? All right. Whack it! Oh, yeah. What do you think? I'm glad you didn't miss. Seriously? Not bad, huh? Yeah. Why? We got one person that thinks, and letting the rest of you form an opinion. Lead is absorbing the shock. It is a little soft. But it's not completely soft. What do you add? You are correct. Very good. If this were to go right to my hand, that would break some bones. Because my hand would require exerting a force back on the hammer to stop it, right? To slow it down. So my hand would get a force directly from the hammer. Well, instead, I hit the brick. This force tries to make the brick move. The brick is what's in contact with my hand. It's the brick that tries to make my hand move. Does this move much, though? Why? Because it has a whole lot of mass, so it has a whole lot of inertia, and it resists changing its motion because it's so massive. If I did this with a lighter brick, this would move this, and this would move significantly into my hand, and now it would hurt. It's because it's big and massive and has lots of inertia. But it's still forces causing changes in motion. And again, back up here in the corner, it matters what the force is being acted on. This is acting on the brick. It's the brick that's acting on my hand. And this isn't moving much. It's not accelerating much. I'll end with that one. Have a great break. Mini break.